Today we're going to demonstrate the concept of center of mass and rotational movement of bodies. In another segment we spoke about how the mass of an object can be treated as if it's concentrated in a center of mass for the analysis of its motion. And this includes not only motion from one place to another, but also includes the rotational motion of a body, that is the angular rotation and the angular momentum that's implied there today. Today we're going to be throwing two hammers that have different centers of mass to them. We're going to be tossing just an ordinary roofer's hammer here, and the yellow tape here points us to where the center of mass is. It's not perfect, but it's about there. You can see that's balanced there. And then we're going to be tossing an 8-pound sledgehammer, and I've also marked the center of mass to where it is over here. Okay, so let's throw some hammers, shall we? The first rule is that the motion of any object, whether it is rotating or not, can be described by following the motion of its center of mass. If there is rotation, it is about the center of mass. This is true no matter where on the object the center of mass is. In the sledgehammer, the center of mass is very close to the head, and the handle rotates around the hammer's head. In the roofing hammer, the center of mass is away from the head, further down the shaft. The hammer's rotation is still about the center of mass, but now the head and handle both rotate around it. This makes an object's rotational motion a bit complicated. Let's slow it down. If we track the motion of the center of mass in blue, we see that its motion follows a simple arc. But if we track the motion of the handle in green, its motion seems to be in fits and starts. The relative motion is made clearer if we follow the trajectories with one camera location. Again, the motion of the center of mass is indicated in blue and that of the handle in green. You can see that both the head and the handle have forward motion. Again, the head follows a simple arc, but the speed of the handle varies with respect to the phase of rotation. Here, the rotation of the hammer is anti-clockwise. Initially, the handle swings forward under the head and its speed is quite fast. Next, the handle's trajectory comes into line with the head's, and at this point both have the same velocity. As the handle swings further, the handle's speed slows down with respect to the head. And finally, the handle swings around again so that its forward velocity is again faster than the head's. You'd better hope the handle doesn't hit you in the head at this point. As it happens, that is precisely what this bird does. The peregrine falcon is one of the world's most impressive avian predators. Its signature maneuver is known as the stoop. In the stoop, the bird dives from a great height, homing in on its prey. It's said that the falcon can reach speeds of up to 200 miles per hour during its dive. This is doubtful, but the bird still reaches impressive speed. Just prior to encountering its prey, the falcon brakes, swinging its body and its claws forward. This adds angular velocity to the claws and gives them that extra oomph, and bam, you have a dead bird. The blow is powerful enough to kill a bird many times larger than the falcon. Peregrines have been known to kill red-tailed hawks, for example. And they do it with physics.